Ultrarapid freezing has long been recognized to provide superior preservation of ultrastructure relative to chemical methods of preservation and cryoprotection. And it's also the only method that's known for capturing events that occur on a time scale of less than a few seconds. Now, cryopreservation of biological systems is not a trivial task for most specimens. Cryopreservation is not a trivial task for most specimens. For a long time, the procedures were very tedious and difficult, and the equipment was quite crude. So the yield of well-frozen samples was very low, and most investigators opted to use chemical methods of cryoprotection and fixation in face of the known artifacts because they wanted to have some reasonable rate of productivity. In the last few years, however, the introduction of refined techniques for sample handling and refined equipment for the freezing of biological samples has made these techniques, has made this particular mode of preservation to be almost routine. And that's what we're going to talk about today. The first part of the talk, I'm going to talk about the limitations of chemical methods of fixation and cryoprotection. And then the second part, I'm going to talk about the physics of ice crystal formation in biological systems. And then I'm going to need a break, and you will probably also, so take a 10 or 15 minute break, and then we'll come back and talk about the 5 methods of cryoprotection, of cryofixation, that are in common use now. Okay. First, we're going to talk about the artifacts that are associated with chemical methods of fixation and cryoprotection. Why would you want to do ultrarapid freezing in the first place? As yet, we have no technique for doing high-resolution studies on intact living systems. We have to be satisfied with freezing the action, so to speak, in some way, and obtain a series of static images of dead cells and try to figure out what's going on in the living system from those. So, given that, what criteria can one use to judge the efficacy of any fixation regimen, given that we have no a priori knowledge of the ultrastructure of the living state? I assert that one can specify a few reasonable conditions that would have to be met by any fixation regimen that you expect to preserve the true nature of the living state. Okay. First condition is that a fixative must act quickly. Fixation regimen. Now, none of the techniques currently available can fix a sample instantaneously. The best we can hope for is that we can stop anything that we want to investigate in the shortest possible time. So how do chemical fixatives, how well do chemical fixatives meet these criteria? Well, any chemical fixative has to enter a cell or a tissue, whatever the sample is, by diffusion from the outside. And diffusion is a relatively slow process. One can do a simple calculation based on a diffusion coefficient of 10 to the minus 6 centimeters squared per second, which is a reasonable value for the small molecules that fixatives generally are. And the calculation shows that a few milliseconds are required for a fixative to completely penetrate a 1 micrometer thick planar sample. And about 1 second is required for a sample of about 40 micrometers thick. This is reasonable. This is pushing it for transient events. Most samples are larger than that, or at least of this order. Now, this is a theoretical calculation. The actual rates, the actual rate of penetration, the actual observed rate of penetration of glutaraldehyde and other fixatives into cells is much slower. It's about 1 to 2 microns per second. Very slow indeed. Now, once the fixative gets into the cell, it has to react. Now, all modern chemical fixatives react with certain components of the cell, of the cytoplasm, to form a rigid three-dimensional matrix. And this takes some time. How much time? Well, a few years ago, George Flady and his colleagues were trying to, they're studying the vesicle-mediated transport of materials from capillary lumen to the abluminal side. And they were doing this by perfusing the lumen with porphyritic peroxidase and watching it move to the other side. And they wanted to capture the intermediate stages of transport of the HRP. So they said, well, let's perfuse with HRP and with glutaraldehyde. Add the glutaraldehyde at the same time as the HRP. And they did that. They found the HRP over here. Put it in here, and it was here when they examined the tissue after fixation, after processing. So they said, well, let's try adding the glutaraldehyde a little before we put in the HRP. So they put it in a second before. And the HRP was still over here. They put it in 2 or 3 seconds before. The HRP still was on the other side of the cell by the time the cell was fixed. But they gradually increased the lead time for the glutaraldehyde. They put the glutaraldehyde in sooner and sooner, or they put the HRP in later and later relative to the glutaraldehyde, I should say. And they found that they had to add the glutaraldehyde. They had to perfuse the glutaraldehyde 9 seconds before they added the HRP, before they could prevent transport of HRP across the cell. That's pretty slow. There have been some actual light microscopic observations made of the time required for glutaraldehyde and other fixatives to immobilize cytoplasmic inclusions. And it seems that 30 to 45 seconds are required to immobilize cytoplasmic inclusions in cultured cells, not large objects, very thin cultured cells. And other workers have found in cells that exhibit vigorous cytoplasmic streaming to metapillar hair cells that various combinations of fixatives require 6 to 15 minutes to immobilize all cytoplasmic inclusions. It's very slow. And in both of these cases, well, in this case, after all the cytoplasmic inclusions had stopped moving, the circulation of the endoplasmic reticulum continued for 2.5 minutes. And in this particular case, the circulation of the endoplasmic reticulum was occurring during the 6 to 15 minute period required to stop everything. So it's pretty clear chemical fixatives aren't of much use in studying relatively transient events that occur on the scale of a few seconds or less. And it's also clear that they don't do a very good job of preserving what we know is there to begin with. We'll go into that in a little more detail later. Okay? Second criterion is that a fixative should immobilize all of the atoms and molecules in the cell, or at least what you want to see. Chemical fixatives fail again on this point. There's no single fixative, no combination of fixatives that's commonly used that can immobilize everything in the cell. Aldehydes will react with anything that has a free amino group waiting from it, but they don't do a very good job of fixing nucleic acids, for example, or most lipids. Osmium tetroxide, on the other hand, will fix lipids and anything else with a double bond, but it's very inefficient at fixing proteins, nucleic acids, and saturated lipids. And this selective reactivity may contribute in large part to the observed slowness of the system. Anything that can't be fixed by the fixative has to be gradually trapped in that matrix as the fixative fixes in place whatever it can. Okay? because not everything is fixed, those particular molecules or structures that are not fixed can and do migrate and change their morphology. Again, we'll go into that in a few minutes. In addition, certain enzymes can remain active even when they're fixed, notably lytic enzymes. And this can lead to problems also. Okay? And glutaraldehyde and osmium, in fact all known chemical fixatives, alter the permeability of biological membranes in such a way that ions and small molecules can escape from any compartments in which they're sequestered and redistribute within the cell or be lost from the cell altogether. It makes localization of these species virtually impossible. Okay. Third criterion is that the fixative should not alter the morphology of whatever you're trying to look at. Otherwise, you haven't gained it. Okay? And we should point out here that simply because the structure looks like it's well preserved, it doesn't mean that it's representative of the natural state. It might not have been there in the sample before fixation. Now, it's been known for a long time that the osmotic stresses imposed on cells and their organelles during fixation can lead to loss of turgidity of the organelles, and this leads to the common wavy membrane contours that's seen in chemically fixed material. The mitochondria and the ER are not turgid, have very uneven membrane contours. Okay. Glutaraldehyde, in addition, has been demonstrated to give rise to vesiculation of the plasma membrane in regions of vesicle-plasma membrane contact. See a vesicle in close approximation to the plasma membrane. And either before or after apparent fusion has taken place, you'll see a number of smaller vesicles in the vicinity. These were thought to be real for some time, and it turns out they probably are not in most cases. Okay? Glutaraldehyde can also lead to the formation of myelin fibers in membranes. There's still people, well, in some cases these may be real. In most cases, again, this is an artifact. Glutaraldehyde can also lead to redistribution of intramembrane particles. We'll have a slide of that. You're all familiar with freeze fracture images, nomenclature and such. Okay. Say that one were to fracture a cell, so that freeze and fracture a cell is a natural experiment. You're going to see a certain distribution of intramembrane particles. Say that in this case it's random. What has been observed in some glutaraldehyde fixed material is there are patches from which intramembrane particles have been excluded, either through lipid segregation or some other mechanism. So it can lead to, and actually these appear as blisters in the membrane. Observed in thin section. And it can also lead to the formation of multivesicular bodies in or near plasma membrane. Again, in some cases these are real, but we're going to have to take a look with ultrarapid freezing techniques and find out which are real and which are fixation artifacts. Okay? Now, all of these effects are probably related to the fact that lipases in the membranes, when they're fixed, are still active. Now, glutaraldehyde can't fix lipids, so here are these lipases in the presence of unfixed lipids churning away, generating lysophospholipids, etc. And it's thought that this is what's giving rise to all these various artifacts. The membrane lips are being chewed up, and they then spew out and form the myelin figures, and the vesicles fuse out of the membrane and form into vesicles in the cytoplasm, extracellular medium, etc. Okay. Glutaraldehyde can also artifactually cause fusion of vesicles with the plasma membrane. Gilkey sits here, many years ago, took advantage of this when she was studying the discharge of trichocysts in, what is it, paramecium? Tetrahymena? Okay. She used glutaraldehyde to stimulate fusion of the trichocysts with the plasma membrane. It can also occur in systems where fusion does not normally occur. Would someone turn on the projector, please? This cell was not pretreated, was not fixed and not pretreated. Yes. The freezing isn't great. You can see that there is virtually no evidence of fusion of vesicles with the plasma membrane. This cell was fixed with glutaraldehyde. On the other hand, before it was frozen and fractured. And you can see there's fusion everywhere. It tends to occur in rows. It's not clear why. But this is one example of the kind of artifactual fusion that glutaraldehyde can cause. Now, freezing was not optimal. The freezing was not optimal. And as I recall, they were hand dipping. But this just points out that glutaraldehyde can cause these sorts of events in systems where they don't normally occur. It turns out that glutaraldehyde, and probably most aldehyde fixatives, require oxygen in order to fix the cell or the tissue. And this isn't a problem if the system is not very large. If the system is less than, say, a millimeter. Okay. If the system is, say, less than a millimeter in its largest dimension, then that isn't a problem. When you begin to exceed that, then as the glutaraldehyde infiltrates the sample, it's going to start using up the oxygen at a rate faster than it can be replenished by diffusion from the outside. And it's going to take the glutaraldehyde a long time to fix structures deep in the tissue, and those structures are going to become anoxic long before the glutaraldehyde gets there. And that's going to produce its own set of artifacts, which we really don't understand, but we've probably been seeing for many years. Okay. Now, because of the slowness and selective reactivity of chemical fixatives, it's apparent that the cellular machinery comes to a kind of grinding halt over time, rather than having all parts of a given region being fixed or mobilized at the same time. This makes it difficult to study transport systems, for instance. You can't tell what was where at any given time relative to something else when each was fixed. Okay. As an example of this, again, direct light microscopic observations have shown that hemanthus chromosomes during division can move as much as half a micron while fixation is taking place. Division is not a particularly fast process. It's been shown that in systems that exhibit vigorous cytoplasmic streaming, 100 microns per second, inclusions may be separated by many microns while fixation is taking place. Okay. And a few years ago, John Heuser and his colleagues were trying to capture the fusion of synaptic vesicles with the plasma membrane at frog neuromuscular junction end plates. And they found that even in the presence of glutaraldehyde, they could not prevent the fusion of these vesicles with the plasma membrane. All they could do was capture the fusion sites after fusion had already occurred. Okay? In the face of all these problems with chemical fixatives, it's amazing that they preserve structure as well as they do. And virtually everything we know because of our observations of chemically fixed material. So they can't be damned completely. But it's becoming very clear that if we're going to refine our knowledge of cellular ultrastructure beyond where we are now, more investigators are going to have to switch to ultrarapid freezing techniques. Okay. Now we're going to talk about chemical cryoprotection and disassociated artifacts. Now, chemical cryoprotectants were originally employed to protect cells during freeze-thaw regimens. Cells would be infiltrated with the cryoprotectant and frozen relatively slowly, say less than 100 degrees centigrade per minute, and stored for a while, and then thawed. And people were trying to preserve the viability of these systems, and the cryoprotectant seemed to work reasonably well. It turns out that these same cryoprotectants do not serve to protect the cells under conditions of ultra-rapid freezing. If you freeze slowly, yes, fine. If you freeze ultra-rapidly in the presence of the cryoprotectants and then thaw, the cells are generally dead. And in some cases, the cryoprotectants actually decrease the viability of the cells relative to no cryoprotectants at all. So the term cryoprotectant strictly is not applicable to the use of these compounds to preserve ultrastructure during ultra-rapid freezing. But since it's so firmly entrenched, I'm going to continue using it. Okay. Now, chemical cryoprotectants may act in any one or all of three ways. First is that they may act by increasing the number of nucleation sites for growth of ice crystals. We'll be talking about nucleation sites in a few minutes during the discussion of the physics of ice crystal formation. The more nuclei there are, the more sites there are for the water in the system to migrate to. What this does is it gives rise to a large number of small crystals. The fewer nucleation sites there are, the more large crystals you can grow. But if there are lots of nucleation sites, then all the water gets tied up relatively quickly in lots of sites. So the ice crystals are very small. There's not much damage. You can also decrease the chemical potential of the water. And this makes it less favorable for the water to enter the ice lattice, even though it's still of lower energy, as energy is not that much lower than the aqueous condition. So this will slow the growth of ice crystals. Third effect is to increase the viscosity of the medium, the microviscosity. This will also slow the growth of ice crystals onto whatever nuclei are present. It would seem that this is the predominant mechanism. It's the increase in viscosity of the medium that is the primary effect exerted by chemical cryoprotectants in protecting cells from damage during freezing. Now, typically, one uses concentrations of 10 to 30% of penetrating or non-penetrating cryoprotectants to preserve cells. We're going to talk about penetrating cryoprotectants first. The most common one, of course, is glycerol. Now, glycerol, if used alone, you simply take a cell or a tissue and expose it to glycerol directly, can cause vesiculation of the endoplasmic reticulum and other internal membrane systems. So once people learned this, they started chemically fixing the cells before they treated with glycerol. This alleviated the problem to some extent, but again, if you infiltrate too quickly, you can still get vesiculation of the internal membrane systems. And I have a slide of that. Okay. Here we have a rat intestinal epithelial cell. This cell was only glycerinated and then frozen. And you can see that there are very few intact and distinct membrane systems left in the cell. All the membranes have been vesiculated. This cell was chemically fixed. It was fixed with glutaraldehyde before addition of glycerol. You see the membrane systems are reasonably well intact and distinct as they must be. Okay. Now, it's been shown that glutaraldehyde can also, you can turn that light on, lead to formation of hexagonal type 2 lipidic particles in membranes. Now, it's beginning to appear that hexagonal type 2 structures actually do exist at regions of membrane fusion. They're one of the preludes to fusion. But in many cases, they've been observed in systems that have been glycerinated, so we're going to have to go back and look again and see which ones are real and which ones are artifact. Okay. And glycerol has also been shown to cause clustering of intramembrane particles. Now, in addition, all of the penetrating cryoprotectants change membrane permeabilities, and you're going to have redistribution of ions in small molecules, just as occurs with fixatives. And also, all of them are toxic cells at the concentrations which they have to be used for cryoprotection for this type of freezing. So, clearly, penetrating cryoprotectants are not particularly desirable for really critical studies in cellular ultrastructure or distribution of various small species. Okay? So one can turn to non-penetrating cryoprotectants, sucrose, polyvinylpyrrolidone, etc. It turns out that cells don't contain any heterogeneous nuclei. They don't contain anything that will nucleate ice crystal formation that is not water. And this is something one would expect. I mean, you wouldn't want a cell to have nucleators. If it got below freezing, the cell would always freeze. It turns out that cells can be supercooled well below zero before freezing actually occurs. We'll go into that in a little bit more detail. So if what seems to happen is that nucleation will first occur in the extracellular medium, in which there are usually particulate contaminants. And these ice crystals will grow and contact the cell, and then somehow, either through aqueous pores or actually a rupturing of the membrane, initiate ice crystal formation inside the cell. So if one has a high concentration of a non-penetrating cryoprotectant outside, one can suppress ice crystal formation outside the cells and thereby prevent nucleation inside the cells. The cells can be supercooled to the point where you can get decent preservation. Now, these non-penetrating cryoprotectants are not without their faults. They can cause cell shrinkage through colligative or usually non-colligative osmotic pressure effects. And this can lead to its own set of artifacts, concentration of solutes, etc. And they also are not all physiologically inert. Polyvinylpyrrolidone, even though it doesn't enter cells, is toxic to many cells. And polyethylene glycol, another commonly used non-penetrating cryoprotectant, can cause cell-cell fusion under certain conditions and in certain cells. So again, non-penetrating cryoprotectants are best avoided. Okay, so much for the artifacts of chemical fixation and cryoprotection. I'm now going to talk about what ultrarapid freezing is, the physics of ice crystal formation in biological systems. Okay, now the accomplishment of ultrarapid freezing is dependent on several factors. One of them is the rate at which you can withdraw heat from the region that you're trying to ultra-rapidly freeze. Another is the initial temperature of the sample. The cooler the sample is, the more likely it is you're going to be successful. That much less heat that you have to withdraw from the sample. And it also is affected strongly by the presence of natural cryoprotectants in cells, which we'll move into a bit more later. Now, what is the physical state of the water in an ultra-rapidly frozen cell? And what is the rate of heat extraction that's required? What is the rate of cooling that's required in order to ultra-rapidly freeze cells? First, I'll define ultra-rapid freezing. I think that the best definition of ultra-rapid freezing is an operational one. The region of interest in a cell or in a biological system has been ultra-rapidly frozen if the ice crystals which have been formed in that region are so small that they don't do any damage visible at the electron microscopic level. Right now, that's the best we can do. And we can't ask for more at this point, given the limits of resolution. Okay? Now, ice crystal formation in ultra-rapidly frozen cells can be described in terms used in classical nucleation theory. Are you all familiar with the flickering cluster model of water? Okay. Water is not homogeneous. At any given instant, if you were to look at the structure of water, you would find some regions, most regions not ordered. There would be some regions which were fairly highly ordered. There can be local fluctuations in the temperature of the water, local energy fluctuations which are equivalent to temperature fluctuations. And there can be clusters of water molecules, which may or may not be ice-like, formed in the midst of non-ordered water molecules. And these clusters are continually forming and dissipating in water above the freezing point. The closer you get to the freezing point, the more there are. Now, in the formation of such a cluster, one can describe the free energy of formation of this cluster in terms of two factors. One, total free energy of formation is equal to the volume free energy, as it's called, plus surface free energy. The volume free energy of the cluster, of formation of the cluster, is contributed by those water molecules in the interior. They're ordered. They don't have to be, but they usually are highly ordered, and they have a lot of near neighbors. So it's energetically favorable for this to occur. So this term is usually, well, is always negative. Those water molecules at the surface have the worst of both worlds. They don't have as many near neighbors as those in the interior. And they don't have the freedom of motion of those in bulk solution. So this term, or the freezing point, is positive. Now, in order for a cluster to be stable and to be able to serve as the nucleus of an ice crystal, this term has to be less than or equal to 0. Otherwise, if it is, then there's a probability that it will stay around long enough to serve the nucleus. If it's greater than 0, the probability is it will dissipate before water molecules can begin to add to it to form an ice crystal. Now, at any given temperature, at some critical size, now the clusters that are formed in all different size categories. And as the cluster gets larger, the number of molecules in the interior increases faster than the number of molecules on the surface. Volume increases faster than the surface area. And at some point, the volume free energy is going to be equal to the surface free energy. And this is called, this size of cluster, the size of cluster required for this to be true at any given temperature is called the critical size. Okay. Now, This is called a nucleus, in nucleation theory, a nucleus composed of the molecules that are being grown as a crystal is called a homogeneous nucleus. So this description is for homogeneous nucleation. If there are particular contaminants present, then this doesn't necessarily hold. A particular contaminant may be stable at all temperatures. But as we were discussing earlier, biological systems don't contain heterogeneous nuclei, as a particular contaminant would be. The nucleation in biological systems always occurs through homogeneous nuclei composed of water molecules. Okay? Now, make a little diagram here. Temperature. Let's get this straight. It's that temperature decreasing in this direction. And over here we have critical size. And as temperature decreases, critical size goes down. This is because the surface free energy is largely entropic in nature. So as the temperature goes down, its magnitude decreases. The volume free energy doesn't change much. So this means that the size that a nucleus has to be in order to be stable goes down as temperature goes down. There isn't as much surface free energy to contend with. And here we have the average cluster size. And as temperature goes down, the average cluster size goes up. The less energy there is in the system, the more likely it is that cluster will be formed with a low relative energy relative to the rest of the system. The point where these cross, we have this condition, and nucleation has to occur. This is the point at which the average cluster size is equal to critical size. Nucleation must occur at this temperature. And this temperature, as near as can be determined, is about minus 40 centigrade. This is called the temperature of homogeneous nucleation for water. Now, it has been postulated that at this interface between the cluster and the still aqueous medium, the surface layer is actually a separate phase. There are systems in which this is true. There are two component systems in which one component is suspended in the other. This is one phase, bulk solution the suspension is in. This is another phase, in the interior of whatever is suspended. And this is the third phase. It's not known that it's true for water, so someone has simply postulated. And in such systems, there is, the behavior of such systems is such that there's a temperature called the spinodal temperature, at which the surface free energy is zero, no matter what the size of the cluster is, or no matter what the size of, well, in that case it has to be no matter what the size of the cluster is. If this is such a system and a spinodal temperature can exist, that would mean that at or about minus 40, the surface free energy would be zero for every cluster, no matter what its size. And again, nucleation would have to occur. Now, it doesn't really matter a lot whether this is a system which can exhibit a spinodal or not. At this temperature, the ice crystals that are formed are going to be very small. What you have to do is get the sample to the temperature of homogeneous nucleation as quickly as possible so you have a maximum density of ice crystal nuclei. Get it there or below. And then once water molecules begin to add to the nuclei and release the heat of fusion, you have to keep the system at or below that temperature. So you can both keep the rate of formation of nuclei, so you can keep the rate of formation of nuclei high, basically. That way you get the maximum number of nuclei and the smallest ice crystals. and the least damage to the specimen. Okay. And the condition in which you have ultra-rapidly frozen the sample, in which you've gotten ice crystals which are so small any damage they've caused is not visible at the electron microscopic level of analysis. This condition is commonly called specimen vitrification. You'll see an awful lot of claims in literature that the specimen has been vitrified. And what is actually going on is that they've gotten ice crystals so small they couldn't see them. Now, it is possible under very special conditions to vitrify very tiny portions of samples or very tiny samples. 300 nanometer or so layers on a substrate can be vitrified by dipping into cryogen, for example. Or tiny droplets, 1 micron diameter droplets suspended in the conductive medium can be vitrified if they're in a thin layer and cooled rapidly. But none of the techniques for which vitrification, true vitrification, no ordered domains, has been demonstrated. None of these techniques are suitable for preparation of biological samples as yet. Okay. Now, how quickly does one have to cool in order to reach the temperature of homogeneous nucleation before a nucleus can appear, or a few nuclei can appear in the sample and initiate movement of large ice crystals? Theoretically, the rate has to be between 10 to the 4th and 10 to the 5th degrees Kelvin per second. Minus 10 to the 4th. 10 to the 5th degrees Kelvin per second. And in those relatively reliable observations that have been made in systems where freezing has been done, the quality of freezing has been observed, and the rate of cooling was measured. It's really hard to do that. This has been confirmed. The rate of cooling does seem to have to be within this range in order to get ice crystals as small as they have to be for successful ultra-rapid freezing. Now, there are some effects of sample and cooling geometry on the probability that you'll be able to attain ultra-rapid freezing. Say here we have a large sample. At present, the only means we have for ultra-rapidly freezing samples is by withdrawing heat through the sample surface. Now, that means that we're severely limited in the depth to which ultra-rapid freezing can be obtained in a large sample, because the conductivity, the thermal conductivity of water is pretty low. And at some point in the sample, you aren't going to be able to withdraw heat quickly enough to prevent early nucleation of ice crystals and their growth. And let's say that that's at this level, at which nucleation begins before the temperature of homogeneous nucleation is reached. Once nucleation has occurred and ice crystals begin to grow in this region, the heat of fusion will be liberated, and that will even further slow the rate of heat extraction from regions deeper than this point. And in general, this depth is 10, 15 micrometers under the best conditions. If things are working really nicely, if things are really optimal, sometimes get to 20, a little more. But it's usually more toward the 10 side. Now, let's suppose that instead of having a very thick sample and we're cooling from only one side, we have a thinner sample and we cool from both sides. In that case, since you're cooling from both sides, you can cool the interior, withdraw heat from the interior quickly enough that, on the average, freeze a sample to about 40 micrometers total thickness on the average. And this is predicted theoretically, and it's observed experimentally. You can get 4 times the depth of one side of freezing in the sample cooled from both sides under optimal conditions. Okay? Now, it turns out that theoretically, If one could uniformly cool the surface of a sphere, one would be able to ultra-rapidly freeze a sphere up to about 70 micrometers diameter. Seven times the thickness that one can achieve in one-sided cooling. No one's found a way to do this yet.
Why is spherical 70 when you said 40?
So that's for a flat slab. This is for a flat sample that's an infinite slab. And in that case, you can do 40 in a sphere because of the geometry and the fact that you're withdrawing all, yeah, they'll uniformly over the entire surface. Okay? Now. Now, we've already discussed chemical means of cryoprotection. We found that they are not optimal. Other means of cryoprotection have been employed. One of these means is very commonly employed, usually inadvertently, and that's drying of the sample. In a few cases, it's been done deliberately. If you dry the sample, you can increase the solute concentration, and this in itself tends to suppress nucleation and growth of ice crystals. But it also causes a lot of artifacts, changes in morphology, if nothing else. Usually, though, it happens as the sample air dries while it's being prepared for ultra-rapid freezing. And this seems to be why people who are just beginning to do ultra-rapid freezing get better freezing than people who have been doing it for a while. They're preparing their samples nice and slowly, and it dries out, and gee, I got good freezing. And they get better at it, faster at preparing the samples, and things begin to look bad because the sample is more hydrated. Okay. Certain systems, notably marine organisms, have high internal solute concentration naturally. And these systems can be frozen well to depths considerably greater than the depths that I just gave. Those depths were for average samples. Some samples, on the other hand, are a little more difficult. Those systems that grow in pond water and have a low internal solute concentration. You can't get away with the depths as great as we were just talking about. And some plant cells contain natural cryoprotectants, so they're nice to work with in that way. You can get really nice freezing again to considerable depths, even greater than in marine organisms, if you're very fortunate to be working with such a system. There's one organism, Denaliella salina, that I know of, there are probably others, that in fact fills itself full of glycerol to a very high concentration. In fact, I used that as a test object a few years ago in some pre-substitution studies because I knew I could freeze it well all the time. Okay. Now, another method which is very promising, and this is the most recent technique to begin to become generally available, is called high-pressure freezing. And what one does is one pressurizes the sample to 2,045 atmospheres, which is about 31,000 psi, in about 50 milliseconds, actually less, 30 or 40 milliseconds, before applying the cryogen. And in this case, one can suppress ice crystal nucleation and growth in samples, if they're a flat slab, up to half a millimeter thick. An order of magnitude larger than you can do at atmospheric pressure. If it's spherical, you can do greater than a millimeter. And this may finally allow us to get at what's going on inside larger pieces of tissue, which have heretofore not been suitable objects for other modes of ultra-rapid freezing.
Did you bring one of those along?
No, they're not portable. They weigh about 1,000 pounds. And there are only two in the world, and there's only one that works.
Are they made by different companies?
No, they're both made by the same company. And I made the one work. Okay, it was actually developed by Hans Mohr in Switzerland. He started in about 1968. He finally got to the point about 2 years ago where it was ready to be made into a commercial prototype. Walters has made 3 prototypes. One is in Mohr's lab, one is in Andrew Stalen's lab at Boulder, one I've been working with. and the other one fell off the loading dock. You're building some more. Okay. Now, once one has the sample ultra-rapidly frozen, you have to keep it cold. If you don't keep it cold, because of the surface energy effects that we were talking about earlier, there are a couple of ice crystals side by side. If you get it warm enough, water molecules can migrate from ice crystal to ice crystal at the boundary. And that means the smaller ones will grow at the larger ones will grow at the expense of the smaller ones, because the surface energy of the smaller ones is greater. So it's more energetically favorable for these water molecules to move over here to the larger ice crystal. So you can ultra-rapidly freeze a sample and warm it, and keep it warm for too long. Then you'll get severe ice crystal damage. So you have to be very careful when you're working with samples. Make sure you touch them only with pre-cooled forceps and that sort of thing. Keep this sort of damage from occurring. Now, it used to be thought that you had to keep samples below minus 100 degrees centigrade in order to
I'm sorry, I interrupted, but when is it that you have to have ultra-cool forces? When are you going to touch these things after they're already frozen?
You are going to have to move them at some point. You have to move them into your double replicate device for freeze fracture, or manipulate them for freeze substitution. At some point, you're going to have to touch them.
Well, they're in a frozen basket.
Generally between sample carriers. But
Okay. Okay. That's new.
okay. Now, for a long time, people thought that you had to keep the samples below minus 100 centigrade to avoid growth of the ice crystals. And that was because people thought the samples were actually vitrified. Now, if you do make vitreous water, and there aren't very many good techniques for doing that, but you find that pure water, when it's vitrified, will rearrange. This is amorphous. This is an amorphous system. No ordered domains detectable. Those will reorder to form ordered domains above minus 130 centigrade in pure water. In biological systems that contain solutes, the estimate was around minus 100 centigrade. There's a little more evidence for that we'll discuss later. But since biological systems are not vitrified, you don't have to worry about the temperature of devitrification. What you have to worry about is the temperature of recrystallization, ER. That's the point at which a system that already contains ice crystals will begin to rearrange to form larger ice crystals. Okay? And for animal cells, this temperature is at or above minus 50 degrees centigrade, relatively high. Now, it turns out that cryoprotectants lower the temperature of recrystallization. The reason people thought that you had to keep samples below minus 100 centigrade was because they were cryoprotecting their samples. They would warm them up, and they would find that they had large ice crystals. So they thought they couldn't get above that temperature, and they thought that meant the samples were vitrified. In fact, no. Cells that contain natural cryoprotectants, like some plant cells, exhibit the same effect. And you have to keep those, let's say animal. Okay. For some plant cells, you have to keep the temperature, like the temperature recrystallization is about minus 70 or above. There are some systems you have to be more careful with than others. Most systems, this is fine, but if your sample contains natural cryoprotectants, so you get a clue for that when you look at the quality of freezing in relatively thick samples, then you want to avoid getting it above minus 70. And these figures were determined largely through, there was one electron microscopical study done. And the best way to do this is to freeze a sample, warm it to a temperature for a given period, and look to see what's happening. And in the one study that's been done within yeast cells, it's found this was the boundary.
The 70?
The minus 50.
Oh, the 50.
Yeah. Now, other studies of this type have been done with light microscopy, but that's still a fairly sensitive measure. You can see phase changes in the sample when the recrystallization occurs. There have been a number of those studies done which confirm this temperature for animal systems and show that some plant systems you have to keep below -7. But this isn't really a problem because virtually every sample preparation technique that I know of calls for manipulation of the sample at this temperature or below. So that's really not a worry. You just have to be careful so you get above it. Okay. Now, what are the artifacts associated with ultrarapid freezing? We've talked about the artifacts that are associated with chemical fixation techniques. The most common artifact seen in an ultra-rapidly frozen sample is that it's not ultra-rapidly frozen. There are ice crystals. Now, when ice crystals grow, they tend to exclude all the solutes. So you have regions, domains that are pure ice, and regions around them that have a high solute concentration. And they've reached what's called the eutectic composition, at which they're going to freeze, even though the freezing point has been depressed by the high solute concentration. So what you end up with is domains surrounded, domains of ice surrounded by eutectic. And this shows up in freeze fracture preparations as, especially if you etch a little bit, by smooth etched domains surrounded by raised ridges where the eutectic is. The eutectic does not etch as quickly. So it's easy to recognize there. In a freeze substituted preparation, what you see is a fibrillar network, a reticular network of the eutectic surrounding holes where there was only water. So this artifact is easy to recognize, and I have some examples of it. I'll turn on the projector, and we'll also see if I've forgotten these slides in the meantime here. Okay, I did pretty fun. This simply shows one of the artifacts of glycerol treatment. Here it is. Okay, these are sea urchin eggs. And in glycerol-treated eggs, one can see single-layered membrane diaphragms between the vesicle membrane and the plasma membrane. Now, for years, people thought that these were real. It turns out that they're a glycerination artifact. And if you leave the glycerol out, you don't see the diaphragms at all. So much for that. Okay. Now, all the samples you're going to see here were frozen on the jet freezer, or one like it. This is the red alga, Porphyridium cruentum. It's a freshwater alga. It's very difficult to freeze well. This cell has been well preserved. The extracellular medium and the cytoplasm both show very fine granularity, indicating very tiny ice crystals. In fact, in this case, it's so small as to be at the level of resolution of this technique. And I don't know if you can see it quite from there. Probably not. But right just at the periphery of the cell, around the outside here, there are small columnar projections. This is a slime layer secreted by the cell. That's the hardest thing to preserve, is slime layers around cells. And in this case, it's very well preserved. This was a very nicely preserved cell. All the internal membrane systems are smooth. The cytoplasm is smooth, and the extracellular medium is smooth. And I have a picture of that I can pass around for those of you who can't see it from where you are. Okay, here it is, and I'll just start it over here. Look at that while we're talking about some of the other things. Look closely at the periphery. You'll be able to see little columns of slime. Okay, here's a higher mag view of a face fracture of the plasma membrane, and you can see that the intramembrane particle distribution is fairly random, and the membrane surface is very smooth. Now, freeze fracture is not the most sensitive method for detecting ice crystal damage, but it is fairly sensitive. And if freezing is not optimal, what one sees is lumpy membranes and ice crystal damage in the extracellular medium. Here you can see smooth domains of ice. surrounded by domains of eutectic. The raised ridges. The sample was slightly etched. But the ice is, can you see over there? The ice has been etched down where it was, and the eutectic domains have remained as raised ridges. And this is a slime layer around the cell here. And you can see it's not nice and uniform and formed as it is in the upper photograph. Okay. Yep, these are a little out of order, but that's all right. This is the marine protozoan Euplotes crassus. It's a very large cell. It's, let's see, 10 microns here would be about from here to here. The cell is a couple of hundred microns wide, a few hundred long, and about 50 microns thick. This is frozen in the jet freezer and freeze substituted. I'll go into freeze substitution a little bit toward the end of the talk. You can see that the cytoplasm has been very nicely preserved. One of the most difficult organelles to preserve well is the nucleus. And there's very slight arborization of the chromatin in the nucleus in this sample. Everything else looks good. Now, I do have samples of these cells in which the chromatin is well preserved, but they don't have a nice oral region right next to them like this, showing the preservation of the ciliary arrays, the oral region. And these are cirri, which the bees uses to crawl, if you want to think of the beast as crawling. Okay. This cell was well preserved. This cell was not. And you can see this region near the surface was reasonably well preserved. And as you go deeper into the cell, the ice crystals start getting larger and larger. You can see that the clear spaces are where the ice crystals were, and everything else is the eutectic, the reticular network. Then there's a very sharp boundary here. Now, this is not what one typically sees if the freezing was bad to begin with. And one, I would expect to see this continuing, a progression of ice crystal sizes from here on back, if the freezing were bad to begin with. I think what happened here was, and this is the only time this has ever happened to me, what happened was I warmed this sample up before substitution was complete. And as I warmed it up, the ice crystals began to grow very rapidly, and I got this severe damage. So this is the sort of thing that happens if you warm for a long time.
How much did you warm down?
I warmed up to room temperature.
Oh, a lot.
Yeah.
Okay.
Okay. This is the marine brown alga Felvatia fastigiata. It was on your coast here. And this cell was very well preserved. You can see the smooth membrane faces on the many vesicles in the cytoplasm and the nicely preserved Golgi. This fenestrae and all the associated vesicles. This cell was not so well preserved. It's not so awful you couldn't get any information from it, but you can see that the membranes are a bit lumpy. And the cytoplasm is not as smooth and uniform as it is in this case. Here you can see small areas of eutectic. The freezing wasn't so bad here that there are large bands, but there are small areas of segregation, which you can see in the cytoplasm. Okay, this is a rat lymphocyte, or these are rat lymphocytes. This cell was well preserved and then freeze-dried. And even in this cell, where preservation is overall very good indeed, even in the nucleus, you can begin to see some slight arborization toward this side of the cell, indicative of slight ice crystal damage, a gradient of freezing. And I should mention that with every ultra-rapid freezing technique I've ever used, there is gradation of freezing quality not only with depth, if you exceed the maximum depth for any technique, but also laterally. If you have a flat slab that's been frozen, say you've done jet freezing from both sides, even if you have uniform freezing from one side to the other in a given region, laterally you can find variations in the quality of freezing. And it's sometimes quite striking. You can have an area that looks really nicely preserved here, and 10 microns away it looks pretty bad. Yes?
Given what you were just saying, could you have predicted this polarity of vaporization from the way you froze the sample?
No. I don't know how this cell was oriented. In some systems you can deliberately orient the cell, know which way it was oriented when it was frozen, look at it later, and then get an idea of the depth. But I've done very few systems in which I had that kind of idea of the orientation. I've done largely single cells.
But this one is the flat slab approach.
This was a flat slab approach, yes. And in this particular case, preservation happened not to be good here. This may have been one of those, this is one of those regions where preservation simply wasn't good.
But just to pursue one more step, were the cells that were more towards the edge of the slab generally better preserved than those, say, in the inner part of the body micron zone, or whatever the zone might have been? Or did each cell have its own difficulties?
Okay. Since it is an inhomogeneous system, you would expect to see some inhomogeneities in the freezing in both directions. In general, the inhomogeneity in freezing, as long as you don't exceed the critical thickness for the given sample, the inhomogeneities through the slab, say here is the boundary of the slab, top and bottom boundary. The inhomogeneities this way are not as great as the inhomogeneities this way. I don't know why, but that's been found with every method of ultra-rapid freezing. Now, when freezing is really good, most areas are really nice. Then as the freezing quality goes down, more and more poorly preserved areas appear laterally. And then you'll finally reach the point where you do begin to get poor preservation with depth. I have no good explanation for that. It's simply an empirical observation. This cell was not frozen very well. You can see extensive arborization, not really as extensive as in the previous example, but arborization all through the cell, especially in the nucleus, which again is the most difficult organelle to preserve, presumably because of its salt content. In fact, the chromatin does not seem to be a cryoprotectant. Okay, well, that's it. Well, almost it for this portion of the talk. Let's see how ultra-rapid freezing stacks up against chemical cryoprotection, or chemical fixation and cryoprotection. Okay, we specified that a fixative has to act quickly. Well, at the rates required to achieve ultra-rapid freezing, it's clear that in the samples in which you can be successful, everything is frozen in a few milliseconds. And that's as fast as we can hope for at the present. You have to have everything frozen in a few milliseconds or you're going to get ice crystal movement. Like 3 to 5 milliseconds at the most. And it's been confirmed that the freezing occurs within this time period, in some cases within a millisecond. Depends on the sample and the method that you're using. Now, one exception is high-pressure freezing, in which the freezing can go on for a longer time. That's how you get the greater depth in high-pressure freezing. You're suppressing ice crystal growth and nucleation. So you won't have quite the time resolution, but you can do thicker samples. There's a trade-off. There's always a trade-off somewhere. Okay. Now, the fixative should immobilize everything. And as long as you stay below the temperature of recrystallization, ultra-rapid freezing again will do that. All translation is going to stop in that sample when it's ultra-rapidly frozen. Okay? There should be no alteration of the morphology. Well, there are 3 artifacts associated with ultra-rapid freezing. One, we just discussed, is ice crystal formation, in which case you haven't gotten ultra-rapid freezing. But that's easy to recognize. Another artifact, now let me just these down. Okay, this one is easy to recognize. The second artifact that can occur is drying of the sample while you're preparing it for ultra-rapid freezing. And sample preparation is a limiting factor in every ultra-rapid freezing technique now. If you can't keep the sample healthy, it doesn't do you much good to ultra-rapidly freeze it. But again, drying is fairly easy to avoid if you keep close watch on the conditions and work at a reasonable speed or work in a humid atmosphere if you really have to. Okay? The third artifact is recrystallization of the ice in the ultra-rapidly frozen sample. And again, This is easy to recognize, as the ice crystals, and it's easy to avoid. You just keep it cold. It's to be safest below -70 for any sample, no matter what it is. Yeah, that's pretty easy to do.
Are you
And-
going to talk a little later about how long for various things you think that you should be below -70?
Yeah. Essentially, until the sample has been processed by freeze fracture, if you're doing that, or the sample has been completely substituted, you want to keep it below. Even that isn't rigid. Yeah, we'll go into that. Okay. Now going to talk about the methodology of ultra-rapid freezing. To accomplish the rates of heat transfer that are required for ultra-rapid freezing, there have been two basic methods used. One is to rapidly bring the sample into contact with a cold metal block. And in the early stages of development of this technique, you literally put the sample on the end of a stick, and here's your sample. And by hand, you jammed the sample onto the cold metal block. This takes advantage of the very high thermal conductivity and heat capacity of metals. You can get very rapid cooling at the surface of the sample this way. Also, you can do significant damage to the sample this way. There have been many simple variations tried on this theme. One is just ramming by hand. Another is cooled copper blocks on pliers. Snap the sample, and you can get surprisingly good preservation this way. They generally, at the very surface anyway, it cools quickly enough that there's no, there's minimal shearing and crushing. Starting about, well, in 1964, Van Herreveld and co-workers decided to refine the cold copper block freezing technique, or cold metal block freezing technique, and they developed an apparatus which brought the sample into contact with the metal block without crushing it. They brought it into contact and held it there. Now when you do that, when you have some mechanism for stopping the sample, stopping the movement of the whatever is holding the sample before it gets crushed, you have to make sure that the sample doesn't rebound from the block. Because in that case, what happens is you slow the rate of freezing. It continually makes contact and then pulls away. During the times when it's not in contact, the rate of heat transfer is going to drop greatly, and the depth of freezing will not be very great. And if things aren't quite properly set up, what will happen is the sample will contact the block, freeze a thin layer, pull back, smash against the block again, crush pulverize the layer that was initially frozen, freeze the next layer, pull back, crush, 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 and you end up with rubble on the surface of the sample. But the technique is now to the point where it is possible to bring the sample into contact with the block and keep it there and not cause any artifacts due to crushing or shearing, lateral movement, and that sort of thing. One can end up with well-preserved and non-distorted samples. And one can cool the copper block to liquid nitrogen or to liquid helium temperature. Now, liquid helium is somewhat more expensive to work with, and if you're going to use that, you want a very efficient system, and we make one. The theoretical improvement in freezing is a 50% reduction in ice crystal size and going from a block at liquid nitrogen temperature to liquid helium temperature. Yeah, and in fact, this seems to be the case. This seems to be the observed change. I should say that the temperature, the rate of cooling changes by that much, and the ice crystal size seems to change by at least that much.
What is the temperature of helium?
The temperature of the helium is 4 degrees Kelvin. The temperature of the block is generally around 15 or 16. It's very difficult, unless you do cryopumping, to get the block down to actual 4 degrees Kelvin, but you don't really gain a lot. anyway, because as soon as the sample contacts the block, even if it were 4 degrees Kelvin, it's going to warm up. And what you want to do is keep the block at as low a temperature as you can, say between 16 degrees Kelvin and 40 Kelvin, in order to take advantage of the very high thermal conductivity that metals exhibit at those low temperatures. Okay? So if you're going to do work that is very demanding, very critical, you have to have the utmost in resolution. Then you would probably want to go to a helium system to take advantage of the slight decrease in average ice crystal size that you would get. It may not show up in the morphology that you can see in a micrograph. It may show up, say, in an X-ray diffraction pattern or something like that. But it will be there. And I have some slides of some modern devices. There you go. Okay. This is the medvac freezer. Whoops. I need this. This is the latest incarnation of John Hueser and Tom Reese's and Dennis Landis' machine. And we have is a plunger, a stick on roller bearings, so that it can accelerate quickly when it's released. We have a freezing head, which has the sample backed by some material that's elastic. You can use a piece of fixed lung tissue, you can use foam, you can use springs. There are lots of things that are used, and they all seem to work. And in this type of a system, you can also stimulate the sample in various ways. You can have a muscle preparation or a nerve preparation here, run wires down, and stimulate it at some point during the fall. Now, this technique is very good for doing timing studies. Because in the metal block method, you know the rate, you can time the rate at which things fall. You know where the sample is, and you know when it's going to hit that block. And you can stimulate, if you're doing electrical stimulation, at some point during the fall, and therefore have a known interval between the time of stimulation and the time of freezing, and get very good time resolution on rapid events. And this is the only method that's really well suited for doing studies in the millisecond to tens or hundreds of millisecond range of transient events by ultrarapid freezing. Okay? One can also do other types of stimulation. One can rig up systems to spray some kind of an activator onto your cells as they're falling down if you want to stimulate some metabolic process. Or you could probably rig up something to actually inject a small quantity of liquid containing an activator or some other effector. Okay? At any rate, there is a shutter over the copper block, over the metal block in most systems. Some systems use vacuum. There's a shutter to prevent condensation of atmospheric moisture on the block surface. If you get a layer of moisture or a layer of any contaminant, it's going to be less conductive than the metal. The freezing rate will drop, and you're going to have damaged cells. Okay? At any rate, this particular system and most of the others, actually all the others that I know, are set up so that there is a shutter over the block, and the shutter moves aside at the last moment, if you're lucky. In general, it makes a few times you lose your sample, but in general, the shutter gets out of the way, and the sample then contacts the block. Now, you have to keep the distance that the sample passes through the cold gas as small as you can. If it passes through the cold gas too quickly, you can get the pre-freezing artifact. This can also be observed with other techniques where you have the sample passes through a region of cold gas. What you see in that case is the outer few microns of the sample are very poorly frozen because they've frozen slowly while passing through the cold gas. Then the sample contacts whatever you're using as the heat exchange medium, the cold metal block or the cryogen, whatever, liquid cryogen. And so since you have ice on the outside, ice is a good conductor of heat, and the next region freezes well. And then deeper than that, you can't withdraw heat quickly enough to prevent ice crystal formation, so you have ice crystals. So you get ice crystals, well-frozen material, and ice crystals, a three-layered effect. If you pass through a region of cold gas, or otherwise generate a pre-freezing artifact. Okay, what else can I tell you? Okay, in this system, the mechanism for preventing rebound is an iron ring that is captured by a magnet down here. That plus an optimally tuned system, backing, shock absorber, the film or whatever you're using to back the system and keep it from being crushed. So if that's optimally tuned, then you get no rebound, at least no evidence of rebound. And you also get no crushing of the sample, no shearing of the sample. There it is in action. I don't know what the hand is doing in there. You know what the hand is doing in there, Carolyn? This is Carolyn. That sounds about right. Okay. Okay. This is another device. This is a device developed by Owen Boyne. It's called the Gentleman Gym. And it uses a somewhat different mechanism for keeping the sample pressed against the black. In this case, it works the same way otherwise, but in this case, the striker, the anvil that actually holds the probe that has the sample on it, has a plunger. He calls it a damper here. This plunger pushes on a column of glycerol, which has passageways leading to two other compartments in which there's glycerol and air. When the striker comes down, the probe hits the copper block, and the striker stops. The rebound is prevented because the damper keeps moving. The damper is pushing on the glycerol, and the damper moves down and compresses the air in the side compartments through the glycerol long enough to keep the striker from rebounding. And then the system resets afterwards because these air bubbles push the damper back up. But in this case, it's a dynamic sort of system, in that you're using a moving mass pushing down on the striker to keep it from rebounding. Okay. And there are several types of sample holders that you can use. One for preparing samples for freeze fracture, one for freeze substitution, and then another stub if you want to do frozen thin section. And you can do that with virtually any of the devices that are available. Okay. Let's see what's next. All right. Now, drawing on board. That's one major technique, using a cold metal block. The more common technique is to use a liquid cryogen of some sort. And in this case, you want to move the sample rapidly relative to the cryogen in order to maximize the rate of heat transfer. All of the cryogens that are used are gases at room temperature. What happens, here you have the surface cryogen. Here's your warm sample coming in. When the sample approaches the cryogen, or the cryogen approaches the sample, depending on how you're doing it, before contact can be made between the sample and the cryogen, radiative transfer of heat, here's IR radiation, radiative transfer of heat will vaporize the cryogen around the sample. And this vapor barrier, this gas that's formed, is a very poor conductor of heat. And if that barrier does form, then the freezing is going to be very poor. You simply can't withdraw heat quickly enough to get good freezing in more than, say, the outer fraction of a micron of the sample. So what you have to do is somehow move the sample very rapidly relative to the cryogen to get rid of this barrier, sweep it away, as it were. You also want to use a cryogen that has a high boiling point and a low freezing point, so that you can absorb a lot of heat before the boiling occurs. And you want the cryogen to also have a relatively high heat capacity and high thermal conductivity. Now, the best cryogen that has been in common use is propane. liquid propane, propane near liquid nitrogen temperature. Propane boils at minus 40. It freezes if it's pure at minus 190. So it can absorb quite a lot of heat before it boils. And you can, in fact, supercool it to near liquid nitrogen temperature for a few minutes. If it's pure, you can get it there for about 5 minutes. If it's commercial grade propane, which has a relatively high concentration of impurities, you can keep it there for about 20 minutes. Okay? It also, of all the common cryogens, has the largest effective thermal capacity. That's not the term I'm looking for. But at any rate, its combination of heat capacity and thermal conductivity is the best of all the commonly used liquid cryogens, and is not particularly dangerous to use as long as you keep it cold. Okay. Now, what's that? Okay. Now, the simplest method of accomplishing the relatively rapid movement of the sample relative to the correction is to simply put the sample again on the end of a stick and jam it in by hand, as is commonly done, or on some sort of a mechanism that accelerates the sample on a spring or pneumatically or with a solenoid, whatever. You can get up to reasonable rates, not really high rates, but rates high enough that with a sample prepared appropriately with the proper geometry, you can get ultra-rapid freezing to a depth of a few microns. Say about 5 microns, if you're lucky. Or plunge or quench freezing. As this is called. Okay. And you do have to be very careful to get it through the cold gas layer above the cryogen. This is where the pre-freezing artifact is most commonly observed. And the optimal shape for the sample turns out is have a very thin layer of the sample between two metal specimen carriers. And looked at end-on. For plunge freezing, those would look this way, like this. And with the sample in between. This is a cross-sectional view end-on of the metal specimen carriers. Carriers that have been developed are looked at from the top. Would look like this. And they would move into the cryogen this way. And this section would be through here. It would be two pieces of metal, one sandwiched on top of the other, the sample in between. Is that clear? And this way, you've streamlined the sample so that you can get maximum flow over the surface of the metal and get maximum rate of transfer, or maximum rate of replacement of the cryogen, sweep away the vapor barrier, and manage to accomplish a rate of heat transfer large enough to get freezing in a sample of about this thickness. Now, this is suitable mostly for small cultured cells grown on some kind of a substrate, like a microscope grid with a form bar coating, or cells grown on a glass cover slip, or cells grown on the surfaces of the hats, if the hats are non-toxic, you make them with gold nickel alloy or something like that. Suspensions of cells, you would have to use a sandwich technique. If they are grown on the grids or on a non-conductive surface, you can sometimes hand dip. It's the simplest and cheapest technique, and if your system is small enough, then it's the first one you should try. it might work. If it does, you're lucky. You've saved a lot of money. And there are also a number of commercial devices available to get the sample into the cryogen for you at a good high rate and avoid the vapor, the cold vapor above the cryogen and so forth. That's the simplest and most common method of moving the sample relative to the cryogen. Okay? Another technique is to put the sample into a commercial airbrush. I actually don't know how these are constructed, but this would be a good guess. You have the sample in here, you have air or some gas, nitrogen, passing through it there very rapidly. The Venturi effect pulls the sample into the rush of gas and vaporizes it, converts it to a very tiny droplets. And you then spray these very tiny droplets. The droplets are less than or equal to 10 microns in diameter. You spray these droplets into liquid propane at a fairly high velocity. You generally use 4 to 10 atmospheres pressure. This is just a commercial airbrush. Put your sample in there and spray it into the liquid propane. And you're taking advantage here of moving a sphere rapidly through a cool medium. And you can get very nice freezing. I should mention that the rates of cooling that one typically attains in, or that one seems to attain in cold metal block freezing are about minus 50,000 degrees Kelvin per second. In hand dipping, plunging or whatever, they're about 1 to 2 times 10 to the fourth. Not as fast as one would like, but fast enough to get ultrarapid freezing in a thin enough sample. In this technique, the rates exceed probably 100,000 degrees Kelvin per second. So you can get the fastest known cooling. But there are some problems. I think I actually have a slide of this. Okay. Pointer. Now, here we have the airbrush. Here we have the propane at minus 190 centigrade or whatever temperature. Spray the sample into the propane, and you end up with lots of tiny droplets. You end up with dust suspended in the propane. You then use a pump to draw off the propane at low temperature. You warm it to about minus 85, and this is a device sold commercially by the Vultures Corporation. It has one holder in which you spray. You freeze the sample, and then you transfer this block to a controlled temperature block at minus 85 and draw off the propane. You then add a binder, butylbenzene, which remains liquid at minus 85 centigrade but doesn't begin to substitute the sample during the time that you have it liquid. You make a paste of your sample in the butylbenzene. You have dust in the bottom here, and you just make a little paste of it. And you then transfer small droplets of this paste to waiting specimen carriers and dip them in liquid nitrogen, which freezes the butylbenzene. And you have a sample that you can do some things with. Now,
Can you substitute from that
you could substitute from that.
without going into
I wouldn't put it in the butylbenzene, though, if you're going to do that. There'd be no reason to do that. I would go directly from the powder.
So you would go from the powder right into your substitution.
Yeah. I just pour the substitution medium into
Right
here.
in there.
Now, this technique, unfortunately, is of limited usefulness. If the cells are too large, if they approach the droplet size, it turns out that the airbrush acts like a miniature French press. Unless the cells are very small or protected by a rigid cell wall, the shearing forces that they encounter going through the venturi just rip them up. So that limits the kinds of systems you can work with right there. the number, if you're doing freeze fracture, the number of droplets that you get in any given fracture through the butylbenzene is pretty small. So here you have a large field of butylbenzene with a few droplets in it. Inside the droplets, there aren't that many cells. So the chances of seeing a cell are pretty small. And the butylbenzene, especially if it's not quite pure, often is not frozen at fracturing temperature. It's not, well, it's rubbery. It isn't a hard glass. You try to fracture and it smears and just covers up everything with butylbenzene. You don't see anything. So there are a lot of problems with the technique. We have one of these machines in Andrew Stalen's lab, but it hasn't been used for years. Tried it for a year. It was unsuitable for most of the samples that we used, so we now use controlled temperature block to do free substitution.
Well, you were doing single cells, weren't you?
Yes.
And it didn't work good.
No, because of all those problems. Now, damage to the cells. If the cells survived, very few cells to be seen, etc. It was just too frustrating. It really wasn't worth it. So we went on to develop the propane jet freezer. Okay. Let's see what the next slide is. Okay. These are somewhat out of sequence. Yeah. Let me raise this for a moment. Put it back down. We turn off the light. Now, so that's spraying the sample into the cryogen. Propane jet freezing, we spray the cryogen onto the sample. Now again, the best method of sample preparation, the best type of sample preparation that I found is a sandwich preparation, the sample between two thin metal carriers. You have metal carriers which are shaped like Panama hats. They look like this from the top, and in cross-section they look like this. And take one of these hats, place the sample on it, and then put a thin spacer on top of the hat and on the sample. The spacer serves to keep the sample from being crushed when you make the sandwich. And put the other hat on top, and that completes the sandwich. You then place the sample sandwich between two jets, two cryogen jets, and you spray cryogen onto the sample, into the inner surface of the hats. And because the cryogen is moving so quickly, the rate of heat transfer is much more efficient than in simple plunging. In our propane jet freezer, the cryogen is moving at about 100 meters per second. It's awfully hard to plunge at 100 meters per second. And what this does, of course, is it sweeps away any vapor barrier that's formed and very quickly replaces the warmed propane during those crucial first few milliseconds in which you have to cool the sample. The actual duration of the blast in our machine is about a half a second. And all that the time after 5 milliseconds serves to do is cool down the surroundings so the sample doesn't warm up after you take it out of the machine. The level of liquid nitrogen is controlled by a level controller sensor set at the level that you want the nitrogen to be. The liquid nitrogen cools a metal cylinder. When the metal cylinder is cool enough, we admit propane, and I've recently found that one can use Freon 12 or Freon 13 and get decent freezing in this machine if you really don't want to use propane. You admit the cryogen into the cylinder, it liquefies and pretty much fills the cylinder. Meanwhile, you're preparing your sample, which, as I said before, is the limiting factor in any of these techniques, both in the time that it takes to prepare the sample and the effort and thought that it takes to make sure the sample is healthy by the time you get it in the machine. By the time you've finished preparing the sample, the machine has generally been ready for a long time. That is, the cryogen has been cooled to operating temperature, whatever that might be. Liquid propane, I use minus 190. And in our current device, I should say, we have cartridge heaters in the cylinder wall to keep the cryogen from ever freezing. In the earlier models, that was a problem. You had to work fast. Otherwise, you'd get your sample over there, press the button, nothing happened because the cryogen is frozen. This never happens in the new machine. At any rate, once the sample is ready, you put it between the jets. There are just two tubes projecting from this cylinder, open at the bottom, and you pressurize the cylinder to 10 atmospheres with gaseous nitrogen. And this drives the propane or whatever cryogen you're using out of the jets and sprays it onto the sample. Very simple system.
Now, where's your specimen holder?
The specimen holder would be sticking in here like this. Okay. Oops. So, yeah. Okay. Here is a picture of the machine itself, just like the ones in the hood over there. There is the gaseous nitrogen solenoid valve. There is an RTD temperature sensor, which is used to run the temperature controller which drives the cartridge heaters. Cartridge heaters are in this cylinder wall. This is the cylinder in which the cryogen is liquefied and kept above its freezing point. Here's the propane inlet valve. It's a chuck valve, so that when the cylinder is pressurized, nothing can go back out through the cryogen inlet, propane inlet, and the liquid nitrogen level controller. Okay, here's the liquid nitrogen doer and the little cart that it rolls in and out on. And this is the sample holder insertion port. Here is the sample holder inserted in the port. You see that? Here is the sample holder with the sample positioned between the jet housings. In the RMC machine, the liquid nitrogen boil off when you're using propane comes up past the jets and then out. The jets are in those housings. That way you keep the jets as low a temperature as you can so that the propane isn't warmed up as it comes through. Next, there we go. This is the sample holder, close up. There is a plastic sample. This is the actual sample holder element out here. It's made of Vespel plastic. It was developed for NASA and the space program many years ago. It maintains mechanical strength at very low and very high temperatures, and it turns out to be very suitable for this application. There's a well in the sample holder, and you build the sample directly in that well. You put in the bottom hat, put on your sample, you put on the spacer, or whatever variation of this technique you want to use. In some cases, you can dip the spacer in the sample. That works. And then you put on the top hat. Then rotate this lever to this position with your thumb, and that brings these forks down onto the sample. As you can see, there's a sample built in here, and that holds the sample in place. You then insert the sample holder into the machine. This ring both stops the sample holder at the port entrance and positions the sample directly between the jets. And there's a magnet here, which you can't really see in this picture. And that magnet closes a reed switch in the sample holder insertion port, which triggers the timer which opens the gaseous nitrogen valve and freezes the sample. So as soon as the sample is between the jets, it's frozen. If you delay, then you get pre-freezing artifact due to the cold gas. That doesn't happen. Remember that? Okay. Now, high pressure freezing. As we discussed earlier, this is a technique for freezing very thick samples. It isn't as rapid as the other techniques in the interior of the sample, although it may be just as rapid in the peripheral regions of the sample. But what it's really going to be useful for is getting at the interior of tissue samples, or large cells, systems that we really haven't been able to look at before with other ultrarapid freezing techniques. And this is a schematic of the way the machine is set up. There is an oil pump, an oil compressor, which pushes oil into a pressure accumulator. The pressure accumulator contains a gas balloon at 250 atmospheres, pre-pressurized at 250 atmospheres with nitrogen. The pressure accumulator further compresses the balloon to 350 atmospheres. This is the way the system stores the energy that's going to be needed to pressurize the sample and keep it pressurized later on. There's a valve which holds the pressurized system, or keeps this portion of the system unpressurized until you want to do the freezing. This portion of the system is basically a cylinder, a double cylinder, with a plunger that spans both cylinders. When you want to freeze, you open this valve, pressurize this portion of the system to 350 atmospheres initially, after this has been charged, And that pushes on this side of the piston, which through the connecting rod pushes on the lower portion of the piston, which is in turn in contact with liquid nitrogen, a column of liquid nitrogen, about 100 mils of liquid nitrogen. The bottom portion of this bottom of the cylinder is cooled to liquid nitrogen temperature in a dewar, and you draw liquid nitrogen in through a check valve by bringing this piston back mechanically. When it comes time to freeze, you pressurize this side. This side is at 350 atmospheres. This has a larger surface area than this side, so this side is at a higher pressure. The force on both sides is the same. It's the same because the surface area here is smaller. The pressure on this side of the system is larger. The pressure is increased to 2,045 atmospheres in this bottom cylinder. The liquid nitrogen is then forced through the high pressure line and into the sample chamber. The sample is held in the sample holder similar to the jet freezer sample holder. It's again sandwiched between two metal specimen carriers. The liquid nitrogen comes in, sprays on the sample, and then exits through two narrow apertures. These apertures are about 40 microns diameter. No, 400 microns diameter, I'm sorry. 400 micron diameter apertures. 100 mils of liquid nitrogen is pushed through those two apertures in half a second. And that's how you generate the pressure in the sample chamber. Now, if you use only the nitrogen to pressurize the sample and freeze it, you don't get very good freezing. We'll go into that in a moment. So what is done is a slug of isopropanol is injected into the line ahead of the liquid nitrogen. It's all very precisely timed. This valve closes, the isopropanol is injected, the liquid nitrogen comes rushing in and pushes the isopropanol onto the sample. The isopropanol pressurizes the sample, then the liquid nitrogen cools it. If you don't have the isopropanol in there, the sample cools before it's completely pressurized and you get ice crystal damage. And there are some temperature curves a couple of slides away, which I'll show you. The forces on the sample carrier and on the sample holder itself, as you might imagine, are tremendous. We had to modify them to get them to work at all. That's why ours is the only working machine. And as they were originally supplied, the sample carriers were standard gold alloy carriers, one of which had a hemispherical depression, the other one had a cylindrical depression. That meant that during freezing, the sample carriers could move relative to one another and could move apart. The sample holder was not as strong as it should have been, and one leaflet was able to move away from the other. The sample holder, in this case, has a bottom portion in which you built the sample and then a hinged leaf that goes over. And you screw that into the rest of the handle, and that holds them together. The leaflets were able to separate, therefore the sample carriers were able to separate, and the sample got blown out from between the hats virtually every time. When we first got the machine, we froze 14 samples of fish intestinal tissue, ended up with one still between the hats. So we redesigned the sample carrier so that one fit over the top of the other like a cap, a tight-fitting cap, except for one channel through which the pressure could get in. You had to have that there because if the caps were too tight, the sample would be pressurized and freezing would be lousy. And we also bolstered the sample holder so that both sides were the same thickness and they couldn't spring apart as much. Under those conditions, we were able to keep distilled water between the heads. So that was an improvement right there. Let's go on to the next slide. These are photographs of the device itself. It's about 5 feet high and 3 feet thick and 5 feet wide. And this is the freezing chamber, the sample chamber. And this is the pressure accumulator. This is the oil pump. This is the low pressure side of the cylinder and the low pressure line coming in. This is the dewar vessel containing the high pressure cylinder. You can't see it in here, but there are the high pressure lines coming up to the sample chamber. This is the actual freezing chamber itself. This is the sample holder with its little leaf open. This is the locking ring. You put the sample holder in here, and you put this locking ring in here. It's designed very similarly to the chamber in an artillery piece or a rifle, for good reason. These are ballistic applications of pressure. Both the rise time and the absolute pressures reached are ballistic in nature. You could shoot down a plane with this machine. And here's a system with a locking ring in place. And here are the aperture retainers. This is where the liquid nitrogen comes roaring out, and acoustic dampers. I used the original prototype in Moore's lab about 5 years ago, and you had to wear ear protection if you valued your hearing. It was loud. This system has air stones at the bottom of these tubes, which release the pressure slowly enough in here anyway that it's tolerable to be around it. The machine also has a lot of padding inside. The machine shakes the building. Our prototype has rubber feet, so it isn't as bad. But Andrew was using a prototype that didn't have rubber feet, a year and a half ago. And someone came down from one of the upper floors who was trying to do micro-injection of tissue culture cells. And he had lost several cells in several pipettes. And he was coming down to find out what the hell was going on. He asked them to please tell him when we were going to be running the machine. The new machine does have rubber feet. It isn't quite so bad. But if you have water on the floor and do a run, you can see the surface of the water shake. Beg pardon? There are some people in the lab below Andrews that do electrophysiology of the visual cortex in cats. And they do some very long experiments. They haven't come up yet, so apparently the damping is effective. Okay, now this is again pressure-temperature diagrams showing that here's the rise of pressure in the system. This is rate of fall in temperature if you don't have the isopropanol ahead of the liquid nitrogen. You're down to a point where the sample is going to freeze before the pressure has gotten high enough to suppress ice crystal nucleation and growth. If you have the isopropanol, it delays the fall in temperature just long enough. And during the years of its development, it looked as though we were going to have to be satisfied with not quite optimal freezing that was, say, fair to good. Since we've made the various improvements, the quality of freezing has improved and is now very good to excellent in many cases. So it looks as though this may actually be a viable technique for doing really high-resolution studies in biological systems. Here we have the basic equipment necessary to propane jet freeze biological samples. We have the sample holder itself. We have a pair of forceps. We have 2 rows of Panama hat-shaped metal specimen carriers. 1 row here, 1 row here, 1 pair of carriers for each sample that we intend to freeze. In between those rows of specimen carriers is a row of gold EM slot grids, which we're using as spacers for this particular sample. The spacer serves to keep the sample from being crushed into oblivion between the metal carriers. We also have the sample, which has been spun down into a tight pellet, and a Pasteur pipette, which has been pulled out into a relatively fine angled tip for transferring the specimen from the centrifuge tube to the metal specimen carrier. To prepare a sample for freezing, first pick up one of the metal specimen carriers and place it in the sample holder. We then get a small aliquot of the sample with the Pasteur pipette and apply it to the specimen carrier. The It's necessary to hold the specimen carrier down with the forceps to keep surface tension from pulling the specimen carrier away with the pipette. And you remove the pipette. The sample is now applied to the bottom specimen carrier, and we pick up the spacer and place it on the bottom specimen carrier and the sample and center it if necessary. Then pick up the top specimen carrier and apply it to complete the sandwich. Center it if necessary. We then rotate the thumb lever on the sample holder to lower the forks, which actually hold the sample in place in the sample holder. We're now ready to freeze the sample. That's it. To freeze the sample, the operator picks up the sample holder and holds it like a pistol, with his thumb resting lightly on the thumb lever. Carry the sample over to the jet freezer and insert it into the sample port. The sample is now frozen. Draw it from the port and open the sample holder by rotating the thumb lever to the open position. And then tap the sample holder on the edge of a door which we have waiting nearby. And the sample falls into the door, into a basket under liquid nitrogen, where it's now safe until further processing. We then return the sample holder to the preparation table to make another sample. Under actual working conditions with a real biological sample, one would prepare the sample much more quickly than the demonstration that I just gave in order to prevent drying of the sample in the room air and damage due to the effects of the copper hence. So this would be a more reasonable speed in which to prepare a sample. Close it, pick it up, carry it over to the machine. That's the entire freezing procedure.
Thank you.